Okay, let's have a look at this CIE paper 1 from 2017. Now this is version 3, so that means the paper code is 1.3. If you want the other versions of the papers as well, 1, 2, 4 and 5, then leave a comment down below. Number 1, what is the best estimate of the kinetic energy of a family car traveling at 50 kilometers per hour? Now, of course, kinetic energy is half mv squared. So why don't we say that the mass is about 1,000 kilograms, is about a ton. 50 kilometers per hour. We want meters per second, so well, that's 50,000 per hour. So how many is that per second? What we have to do is divide by 3,600. That's number of seconds in an hour. And that gives us 13.8. So let's just call that 14 squared. So if you do 14 squared times 500, that's half of 1,000. We end up with, well, pretty much 1 times 10 to the 5 joules. So we can safely say this is going to be B. Number 2, what is the magnitude and direction of vector x minus y? So if you do x minus y, then that means we're going across, but we're actually going upwards. So we're going right and up. So we're looking for 8 newtons and 6 newtons. We're looking for the resultant vector there. So we know first of all that it is going to be going upwards from x, so it can't be A and it can't be C, because that would be that vector here, but it's not. And then we just need to find whether it's 10 newtons or 14 newtons. Let's use Pythagoras, square root of that. So that's 64 plus 36, that gives us 100, square root of that, it's going to be 10. Number 3. Which expression using SI base units is equivalent to the volt? So let's just think about what voltage is. It's energy per coulomb. And we don't have any coulombs in here because amp is the SI unit, unfortunately. So we're going to have to go for current times time. So that's IT. Energy, well, work done is force times distance. But then we don't have newtons because that is also mass times acceleration. So turning that into units, we have amp seconds and we have kilogram meters per second squared times meters again, dividing one by the other. We're going to end up with s to the minus 3. So already I can see that it isn't going to be A, B or C, it's going to be D. Number 4, a voltage is carefully measured with a high quality instrument and found to be 2.321 volts. 2 students using 2 different methods concluded the voltage is 2.33 and 2.344 volts respectively. Which statement is correct? All right, 2.33 volts is less accurate and less precise than 2.344. Now, terminology wise, the resolution of your piece of equipment does not determine accuracy, it just determines precision. Because this is a high quality instrument, we can assume that that is an accurate value. So we can see that 2.33 is actually closer to the value than 2.344. So this answer is more accurate than this. So therefore it can't be A or B. Question is it more or less precise? Of course, it's less precise because we're not measuring to that 3rd decimal place. So therefore, even though it's closer to the actual value, it is less precise. So the answer is C. Okay, 5. On a planet, a vertically launched projectile takes 12.5 seconds to return to its starting position. Projectile gains a maximum height of this. The planet does not have an atmosphere. What is the acceleration of freefall on the planet? So let's go from when it's at the top of its trajectory to the bottom, to the ground. So we have S is 170, U is 0 because it starts from standstill at the top, looking for the acceleration, and the time is half of this 12.5 seconds. We're looking for S equals UT plus half AT squared. UT disappears because U is 0. So that means that A is equals to 2S over T squared. So that gives us 340 divided by 6.25 squared. We have an answer of 8.7 meters per second squared. It's B. Displacement time graph for a toy car is shown, which graph shows the variation with time of the velocity v of the car. Of course, if we have a displacement time graph, it's the gradient of the graph that gives us the velocity. So a constant gradient means that we have a constant speed, a constant velocity. But what is it? Well, it's going 2 meters in 2 seconds, so its velocity to begin with is 1 meter per second. So it can't be B and it can't be C because we have a velocity of minus 1 meter per second there. So is it A or is it D? It seems to be this middle bit that's different. We're going in the opposite direction, so our velocity has to be negative for that portion. It's A. A driver stops his car in time t by gradually increasing the total braking force in the car. The graph shows the resultant force on the car, which graph shows how the speed of the car will vary during this time. Well, if force is increasing over time, we can actually just replace that with acceleration or deceleration. We know that speed isn't going to decrease linearly like this. It's also not going to have this inflection in either. It's going to be one of these two curves, but which way round is it? Let's just have a think. We have the speed decreasing very quickly first, and then it sort of levels off. You probably know that if you're in a car and you want to slow down gradually towards the end, you have to ease off the brakes. So it's actually going to be D. 8. The graph shows variation of a quantity y with a quantity x for a body that is falling in air at constant velocity in a uniform gravitational field. Which quantities could x and y represent? X, air resistance, and y is acceleration. Well, no, because there's no acceleration, but there's still air resistance, so that can't be true. B, loss of height, and y gaining kinetic energy. Again, that's not true, because even though we're losing height, we're not gaining any kinetic energy, because again, we're falling at terminal velocity. X, loss of potential energy, y, work done against air resistance. That makes sense. If we're falling, but the energy is not turning into kinetic energy, then it's being used up, as it were, by the air resistance. It should be C. Let's just check. Time and velocity. Well, of course not, because the velocity, again, is constant. 9. A ball of mass, 2 kilograms, travels horizontally with a speed of 4 meters per second. The ball collides with a wall and rebounds in the opposite direction with a speed of 2.8. The time of the collision is 150 milliseconds. What is the average force exerted on the wall? We know that force is rate of change of momentum. So that's delta mv over t. Okay, you might say impulse over time, same thing. So we're going to have that 2 kilograms, but then we need to multiply by the change in velocity. Now be careful, because we are talking velocity, not speed. So it's going to be 4 minus 2.8, because it ends up going in the opposite direction. The overall change in velocity is 6.8. That's divided by the time, that's 0.15 milliseconds. And that gives us 91 newtons, which is D. 10. An ice hockey puck of mass 150 grams moves with an initial speed of 2 meters per second along the surface of an ice rink. The puck slides a distance of 30 meters in a straight line before stopping. What is the average frictional force acting on the puck? Well, first of all, we need to know the energy. And it had kinetic energy to begin with. So that's half times, now this is in grams, so we need to turn that into kilograms. 0.15 times 2 squared. So ultimately that's going to be 2 times 0.15. So that gives us 0.3 joules. So that's the energy that it has, but it loses all of that due to friction. And so this energy, work done, equals force times distance. And we're looking for the force. So force is going to be this 0.3 joules over the distance of 30 meters. And I can see that's going to be a multiple of 10. So that gives us a 11. A uniform beam of mass 1.4 kilograms is pivoted as shown. The beam has a length of 0.6, yada, 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 whatever. What is the torque that must be applied to the beam in order to maintain it in equilibrium? So basically we're just being asked, what is the difference between the clockwise and anti-clockwise torque or moments? So let's find all of these out first of all. So let's go with clockwise first. So we have 6 kilograms pulling down, that's 0.15 away. So I'll tell you what, let's just call this force 6G times 0.15. Do we have any others? No, we don't. So let's now go with anti-clockwise. So we have the mass of the beam, so that's 1.4. And what is this distance here? Well, we know the beam is 0.6 altogether. So this distance here has to be 0.3 from the end to the pivot. So that means this is 0.1. So that's 1.4 G times 0.1, but we have this other force acting here as well. So that's going to be plus brackets 3g times the distance there from the pivot. So let's find the difference in the torque. So let's do 1.4 times 0.1, that gives us 0.14, plus that 3 times 0.35, we'll just forget about the g's for now, that gives us 1.05, and then we take away 0.9, so that gives us 1.19, take away 0.9, that gives us 0.29. However, that is 0.29 g, so let's times that by 9.8, and we end up with a torque of 2.8 Newton meters needed to keep it in balance to make up for that difference. An air bubble is rising through a liquid at a constant speed. The forces on it are the upthrust U, viscous drag D, and its weight W, which diagram shows the direction of relative sizes of the force. Well, if it's rising at a constant speed, we know that altogether the forces must be balanced. Now here we have drag going upwards, but we know that's not true. The drag has to be opposing the movement, so it can't be D. Now we can see from B that these two forces do not add up to the upthrust, so that can't be right. It's an air bubble, so of course the weight is going to be negligible as well, especially compared to the drag. So it's not going to be C because that has a fairly big weight. 13, the diagram represents a sphere underwater. PQRS are forces acting on a sphere due to pressure of water. Each force acts perpendicularly to the sphere's surface. P and R act in opposite directions, yada yada. Which information about the magnitudes of the forces is correct? Well, we know S and Q are going to be equal, fine, because they're on the same level as it were. But what about P and R? We know there's going to be a bigger force, a bigger pressure on the bottom of an object in water compared to the top. So it can't be C, can't be D because they're saying it's equal, and it can't be B because they're saying that P is bigger than R. It has to be A. 14, the first column of the table gives 4 examples of work being done. The second column gives more detail of the action. Which row is not correct? A girl dives from a diving board into a swimming pool, and the detailed work is done by the girl against the gravitational field as she falls. That's not true already, because we know that if you're working against a gravitational field, you're actually going upwards. So it seems like the answer is A. Let's just check the other ones. B, man pushes a car along a road, work is done against friction. That's correct. Electron is accelerated towards a positive charged plate, work is done on the electron. Yes, that's it. Work is done on the electron. Here we have work done by the girl. It's the other way around. D, a piston is pushed outwards as the gas expands. Work is done on the atmosphere by the gas. That's also correct. 15, a steam turbine is used to drive a generator, yada yada yada. What is the efficiency of the turbine? We know that efficiency is useful power divided by input power. So we know that PI has to be at the bottom. So it can't be A and it can't be B. But we're talking about useful energy output power, it has to be D. 16, a constant force pushes through a block along a horizontal frictional surface. The block moves from rest through a fixed distance. What is the relationship between the final speed of the block and its mass m? So we're looking at kinetic energy, but we're saying what if kinetic energy is constant? How are m and v related to each other? They're on the same side of the equation right now, but we want to put one of them on the other side. So let's put m onto the other side. So let's move it over here. But then we want to get rid of all the constants. And so we can say that actually 1 over m is proportional to v squared. Now we don't have any squareds here, so we're going to have to square root it all. So therefore 1 over the square root of m is proportional to v. It looks like it's going to be C. 17, a man has a mass of 80 kilograms, ties himself to one end of a rope, passes over a single fixed pulley, pulls on the other end with the rope to lift himself at an average speed of 50 centimeters per second. What is the average useful power at which he is working? Okay, we know that power is equal to force times velocity. And we know that velocity in this case is going to be 50 centimeters per second, so that's 0.5 meters per second. Question is, what is the force? Well, he's lifting himself at a constant speed. So he just needs to supply the force to overcome his weight. So this is just going to be 80 G, 80 times 9.8. And I can see that if that's basically 80 times 10 times 0.5, basically 800 divided by 2. So it can't be any of these. It's going to be about 400 watts, or more precisely 0.39 kilowatts. 18, two wires with the same Young modulus in cross-sectional A but different lengths are subjected to different tensile forces F. Extension of each wire is the same. The column headings show 4 different quantities. Which quantities have the same value and which quantities have different values for the 2 wires? Young modulus is equal to FL over A delta L, or you might know that as E. Let's call it E for the sake of this question. So we know that if the Young modulus is staying the same, then that means that altogether, but we know that ultimately, in order for the whole thing to stay the same, FL over E has to stay the same in order for Young modulus to be the same. So it can't be A and it can't be B. Okay, let's check out C and D then. The only difference is E over FL. So let's rearrange the equation to have E over FL. So E over FL gives us 1 over AE. Now, we're told that A and E are staying the same for both of them, the area and the extension. So that must mean that the Young modulus over force times length has to be the same as well. It's D. Not the easiest question in the world, that one. Two springs, X and Y, are stretched elastically. Graphs show the variation with extension X of the force applied to each spring. Which statement is correct? When each spring is given the same extension, the energy stored in Y is 4 times the energy stored in X. Now, we know that energy stored in a spring is the area under an Fx graph. So energy is half F. X. So let's just have a look at how F and X are changing. But the statement says if they're given the same extension. So if they're given the same extension, that means that we're talking about 5 for spring X, but of course it's just going to be 10 newtons for that. What's happening when we compare the two? What's happening with the force? That's going up by times 8. Extension is staying the same. So the energy should go up by a factor of 8 as well. But A says that it's only 4 times the energy, so it can't be that. What about B? The energy stored is 8 times the energy. Yes, that is correct. 20. The diagram shows the force extension graph for a steel wire up to its breaking point. What is the best estimate of the work done to break the wire? So we have a force distance graph. So work done is going to be the area under it. So let's figure out this little triangle first. That's going to be 1 times 200 newtons. Yes, we are dealing with millimeters, but we'll sort that out at the end. And we're going to have to divide that by 2 because it's a triangle, and that gives us 100. Here we have this rectangle, 9 times 200, 1,800. And we have this triangle here as well. That's 9 times 50 divided by 2, 450 by 2, that's 225. Add these all up together, that gives us 2025, so that gives us 2125. That's Newton millimeters. Of course, we know we have to divide by 1,000 to get Newton meters. That's okay because we can already see that this is going to be closer to 2.1 joules. 21. Which statement about EM waves in a vacuum is correct? A. Amplitude is inversely proportional to velocity. No, that's not right. Amplitude doesn't factor in really with our EM waves. Frequency is inversely proportional to wavelength. Yeah, we know that because frequency gets bigger and wavelength gets shorter. B looks like it's correct. Let's check T, C, and D. Intensity is proportional to amplitude. Again, we don't really care about amplitude. And velocity is proportional to wavelength. Well, no, because all velocities are the same. Transverse wave travels along a rope. The graph shows the variation displacement. Okay, which distance along the rope do the particles have maximum upwards velocity? So we have a displacement time graph. Now we know the particles are going to be moving fastest at these points here. So it's not going to be at the peak, so it's not B and it's not D. Question is it at this point here or this point here? Bit of a tricky one. We want the particles to be moving upwards. Now if the wave is traveling this way, then in a second, the wave is going to have shifted over here. Where is this particle here now? It's at that point. Where is this particle here? As the wave moves across, these particles are going up, these particles are going down. So it's going to be at 0.5. Bit of a tricky one. 23, a trace is shown on the screen of a CRO. Time base is 2.5 milliseconds per centimeter. Y gain is 2 volts per centimeter. What's the frequency and amplitude of the waveform displayed by the CRO? Let's go with amplitude first. So we're going up 2 squares. Each of those is 2 volts. So we know that it has to be 4. It can't be B and it can't be D because they've given us peak to peak instead. What is the frequency though? Well, we can see that it's not going to be A, can't we? Because that's a tiny, tiny frequency. Let's just check it though. How many squares are we going across? That's 1.5 because 2 waves is 3. We can see that there. So one time period is 1.5, but that's 2.25. So time period is going to be 1.5 times, it's 2.5 times 10 to the minus 3. It's going to give us 3.25 times 10 to the minus 3 seconds. Therefore, frequency is 1 over that. I can already see it's going to be bigger than 1. High-speed train approaches the station. We observe a speed of 80 meters per second. The train's horn emits a sound of frequency 250. Speed of sound is 340. What is the observed frequency of the sound from the horn? So the equation for an observed frequency for Doppler effect is the original frequency times the speed of the waves. So that's 340 divided by the difference in speeds between the sound and the observer. That gives us 330 hertz. Which row shows a correct frequency in hertz for each of the 4 principal radiations? X-rays, ultraviolet, microwaves, and infrared. Now, the only problem with this is that microwaves are the wrong side, so we need to pretend that microwaves are the other side in order for them to be in order. So we want the frequency of X-rays to be the highest, so it can't be A and it can't be B, can't be C either, so it has to be D, just knowing that X-rays has to have the highest frequency. 26, a pipe of length 100 centimeters open at both ends. Loudspeaker situated at one end of the pipe can emit sound of different wavelengths. If it's open at both ends, that means that we have to have an antinode at both ends. The fundamental mode looks like that. That's the first possible standing wave that you can have in there. 50 centimeters. We can fit multiples of the waves in there. At all these other ones, we can't. The length of the pipe must be a multiple of the wavelength. So it can't be B, C, or D. 27, monochromatic light is incident on diffraction grating. Which row shows possible effects of replacing the grating with one that has twice as many lines per millimeter? Well, n lambda equals d sine theta. Twice as many lines means that D goes down by a factor of 2. That means that n will go down as well, because we can see that n is proportional to D. Cross out the wrong one there. So that means it can't be D and it can't be C, because the number of orders decreases. But then we know that the angles must increase if we have fewer orders, so that means that it has to be B. 28, monochromatic light of wavelength lambda, yada yada yada. The nth dark fringe from the central bright fringe is observed at point P on the screen. Which equation is correct for all positive values of n? What we have here is the path difference. In order for us to have a dark fringe, we don't need a multiple of the wavelength. We need it to be a multiple plus or minus a half, so it can't be A either. But let's just have a think about this. If this is correct, then we have 1 plus a half, but we know that we have a dark fringe when the path difference is half lambda as well. Can't be D, has to be C. 29, dipole of a pair of charges, yada yada. In which direction does the force act on an electron when at point X? We know the field lines show the direction of the force acting on a positive test charge. This would be for something positive. This would be for something positive maybe, but C and D show what's going on for a negative charge. We can't have a field line and then suddenly have a force just going off at any random angle. The field lines show the actual direction of the force, so it has to be D at that point. 30, in a uniform electric field, which statement is correct? A, all charged particles experience the same force. That's not true, because they can have different charge. All charged particles move at the same velocity. Again, all electric field lines are directed towards positive charges. No, because we just said that they show the direction of the force on positive charges. All electric field lines are parallel. Yes, for a uniform field. 31, two metal plates are a distance of 30 centimeters apart in a vacuum. Current exists, electrons move at a constant speed of that. At any instant, there is always just one electron traveling between the plates. That's clever. What is the current between the plates? So we want to find amps, so that's coulombs per second, and we have meters, and we have meters per second. So all we have to do is take our charge, 1.6 times 10 to the minus 19, multiply it by the speed, meters per second, that's coulombs, and divide by 0.3, and that's obviously in meters. So we're getting rid of our meters, and we should end up with coulombs per second. We end up with 8 times 10 to the minus 13 amps. One of those times when units are your friend. 32, the diagram shows a portable generator connected by cables to floodlights. The generator produces a current of 10 amps, constant PD of 240 volts. The total resistance of the cables is 2 ohms. What is the PD across and the power P delivered to the floodlights. So first of all, let's just find out the resistance of the floodlights. 240 volts, 10 amps, V equals IR. Therefore, the resistance is going to be PD divided by current. That's 240 by 10. That gives us 24 ohms. So therefore, 1 ohm taken by the cables. This is going to be 22 ohms. P equals I squared R. So that gives us 10 squared times 22. So that's 100 times 22, 2200. The answer has to be B. 33, metal cube has size length A, electrical resistance. What is the resistance between the opposite face of a cube, the same metal with size of length 3A? So we know that resistance is equals to rho L over A. Rho is staying the same, so therefore R is proportional to L over A. So if L is going up by 3, but A, the area, is going up by times 9 because it's 3 squared, because we have a square, that means that overall we're going down by 3, so the answer is C. 34, graph of PD against I is shown. As the cell reaches the end of its useful life, its internal resistance increases and its EMF decreases. Which diagram shows a graph of V against I for the cell near the end of the life? Well, it can't be A for starters, because that shows the EMF is staying the same. Can't be C, because that has the EMF going up. And we know that the internal resistance increases, so we have to have a steeper line. It's going to be B. 35, 20 volts DC, supplies connected to a circuit, yada yada yada. There's a PD drop of 7 volts across L, further 4 volts potential drop across N. What are the PD drops across M, P, and Q? So let's just have a look at this here. We know that the PD drop across here altogether has to be 20 volts. So this has to be 13 volts. So it has to be B or C, can't be A or D. And if we're going from 7 volts, but by the time we get to here, we have a 4 volt drop, that means that P can't be 7. So it has to be C. So that's going to be 11 volts. Again, 20, that's going to be 9 volts. Makes sense. 36, potential divider. Which statement is correct? When R1 increases, it takes a greater proportion of V0, so V decreases. Yeah, we know that's correct. Let's just check the other ones. When R1 increases, the current through R1 and R2 decreases, so V increases. That's just the opposite of A. C, when R2 decreases, it takes a small proportion of V0, so V increases. No, whatever happens to the PD across R2 has to happen to V as well. When R2 decreases, the current through R1 and R2 decreases, so V decreases. No, again, they're doing the opposite. They have to be doing the same thing PD-wise. 37, nucleus of uranium-238 decays. Alpha particle or a beta particle is emitted during each step. What is the total number of beta particles that are emitted? So let's have a look. We need to be going from 238 to 206. So that's 32 difference. And if every alpha particle has a mass of 4, then that's going to be 8 alpha decays. If that's 8 alpha decays, this goes down by 16. So that takes us to 76, but we need to get up to 82 again. So that's going to be 6 beta decays. It's A. 38, which statement about alpha particles is correct? Alpha particles emitted from a single radioactive isotope have a continuous distribution of energies. Nope, definitely not true. They can all have different energies. Alpha particles have less ionizing power. No, they have more. C, the charge of an alpha particle is plus 1.6. No, because they have 2 protons, so it looks like it's going to be D. Speed of alpha particles can be as high as that. Yes, they can be moving very fast. 39, the nuclear equation shows a term missing. What is represented by the missing term? Well, if we have beta minus, in order to balance the lepton number, it has to be an anti-electron neutrino. Finally, 40, which particle is a fundamental particle? It's an electron. Hadrons, neutrons, protons, all made of quarks. That's it. If you want to go on to paper 2, click the cards and I'll see you there.